Speaker today is Professor George Christou from the Department of Chemistry, University of Florida at Gainesville. And Professor Christou will talk today about molecular nanoparticles, molecular route to ultra small nanoparticles of important metal oxides.
But before he starts, let me present Professor Christou. He was born in the Mediterranean island of Cyprus and grew up in London, England. He obtained his bachelor and PhD degrees at Exeter University and did his PhD in organic chemistry under the supervision of Professor Raydon. He did his postdoctoral fellowship with Professor Garner at the University of Manchester and next NATO postdoctoral fellowship with Professor Holm at Stanford and Harvard universities. Both in bioorganic chemistry targeted at molybdenum iron sulfur clusters of nitrogenase enzymes. His first faculty position he took up at Imperial College London in 1982, and he was interested in manganese chemistry then, and that is now continued till today. 2 years later, he moved to Indiana University, Bloomington, and where he rose through all the ranks of professors up to below professors. In 2001, he moved to University of Florida to take up his present position. And at the moment, he is the distinguished professor of that university. His research interest is a synthetic and physical inorganic chemistry of transition metals. He's particularly interested in 3D metal oxo coordination clusters and its application to such fields like bioinorganic chemistry, supramolecular chemistry, nanoscale magnetic materials. He was a pioneer in the new magnetic phenomena we know now as a single molecular magnetism. We already learned what this is from Jakob. And of course, with potential applications to ultra-high density information storage, quantum computing, etc. In bioinorganic chemistry, he has been long fascinated with manganese, calcium, oxygen, evolving complexes that are involved in water oxidation to oxygen during photosynthesis. More recently, he worked also in a variety of other areas like supramolecular chemistry of magnetic molecules and resulting quantum physics properties. Or he is involved in synthesis of molecular cluster of ultra small nanoparticles, like manganites with the perovskite structures, or cerium dioxides, or bismuth, magnesium, and iron oxides. He collaborated with many types of spectroscopics, physicists, including quantum physicists. His work led over 600 peer-reviewed publications. And according to Google Scholar, his papers are cited more than 40,000. And his 8 indexes approaching 100. He's also very committed to as an educator and conference organizer. He founded many students or meetings in Florida and around. And from his CV, it can easily be seen that he's very supportive for young people which are entering the science. Let the Professor Christou, the screen is yours.
Okay, thank you. I hope everyone can see that.
Yes.
Okay, well, first of all, thank you, Paulina, for that very nice introduction. Being in the field for a long time, it's a reflection of how old I'm getting, I suppose. But anyway, hello, everyone around the world, wherever you are. It's a pleasure to be part of this symposium series, Quantum Crystallography and Related Uses. I think I will be, my talk is primarily in that related areas. I'm a very synthetic chemist, also interested in physical methods and magnetism and so on. But my crystallography is as a user, but in areas where absolutely crucial structural information is required. So crystallography has really allowed the field to progress. And I've long been in magnetism, as you heard, but I will actually talk to you about some new areas that I'm in that you heard as part of the introduction, because I've been in single molecule magnets for 30 years or so. And so in the last 5 or so years, I've tried to open up some additional areas while still being aware of possible applications of these new areas to magnetic systems. So I'll take you through that, and you can see where I'm trying to get it to go. On my first slide, though, you can see some nice pictures of Florida. It's an interesting state. Of course, the weather's great, the beaches are great, and some of the cities I love to visit, such as St. Petersburg, which is on the sea, on the Gulf side, on the western side. You can see a sort of a restaurant area where the pier is. You can see the picture from the Salvador Dali Museum, also in St. Petersburg. Not many people know that there's a Dali Museum in western Florida. And this at the top in the middle here is my son at a dolphin sanctuary in Key Largo, in the south of the state, where they take injured dolphins or dolphins whose parent has been killed, and so they keep them there. They look after them. They become very tame, and for a small fee, you can go and swim with the dolphins. So my son did it, and my wife did it. I personally have never done it, but it looks very good. Anyway, so as you've heard, I've worked for a long time in magnetism. I've worked with single molecule magnets. I've worked with, of course, which I didn't discover, was discovered 1980. I've worked with tetranuclear complexes and trinuclear complexes, and I've worked with bigger ones, and I've worked with giant ones where we have molecules with 4 nanometer dimensions. See hysteresis, we see all the things that make single molecule magnets so interesting, and you've heard a lot of additional things in Jakob's excellent talk that preceded mine. And crystallography, of course, was extremely important in this area because with these paramagnetic molecules, there's really no way you can figure out what you have without single crystal X-ray crystallography. And as this field has progressed, of course, the blocking temperatures, the operating temperatures have risen, as you've also read in the previous. Now, a lot of people are trying to put single molecule magnets on surfaces, and with satisfying success, especially with things like the phthalocyanines, which are very robust. With other single molecule magnets, it's not clear to what extent they're distorted by being on the surface or even damaged, because of course you cannot get crystal structures of molecules on surfaces. However, since people are also putting them on nanoparticles or trying to, it's become important, I think, to get more information about magnetic molecules on surfaces. And that was one of the applications, and I'll mention this in my talk near the end, for the second half. That's one of the reasons that I started this new project some 5 or 6 years ago, in which I will spend the first half of my talk describing to you. There won't be any magnetism in this, but it's the foundation for a lot of the work that I'm doing at the moment. So I'll explain where it's going. So the field I became interested in related to one of the, shall we say, limitations of nanoparticles, traditional nanoparticles, and the fact that you cannot make a sample of nanoparticles that contains exactly the same size and shape particles in it. There's always a distribution, both in size and in shape for that matter. It doesn't matter if you're working with larger nanoparticles, 50 nanometers, 100 nanometers, 500 nanometers. But when you get down to ultra small sizes, less than 20 nanometers, maybe less than 10 nanometers even, then a size distribution, even a shape distribution, becomes a problem. Because the properties become very sensitive to size and shape. And so you never really have one type of particle there that will respond in a specific way to an external magnetic field or whatever. You have a range, and you're always looking at the cumulative properties of everything in there. And even when you see something like this figure at the bottom, on the right-hand side, this is what you might see in a TEM, and you think, well, I've got single size or monodispersed material. But in fact, you probably have a shape distribution too. And so the properties will be very, very different. And this is actually for cerium dioxide, and the properties of these shapes really do differ dramatically. So that's the challenge. The synthesis of truly monodispersed single-sized nanoparticles and their structural characterization to atomic resolution are extremely important challenges in nanoscience. To overcome such challenges, what do we need? Well, we need a way to make truly identical, in other words, what we call monodispersed single-sized nanoparticles with identical shapes too. And we also need a way to characterize them to atomic precision or resolution. And things like TEM may give you an idea of your particle, but they don't give you much information about the surfaces and the sort of surfactant or ligand shell, which the surfaces, of course, are where a lot of the catalytic activity is, and also where catalytic metals are deposited, and also magnetic units. So this is important. How do you overcome such challenges? Well, after some quarter of a century in single molecule magnetism, which you can think of as an area of nanomagnetism, except the single molecule magnets don't actually look like pieces of metal oxides, remember, we realized that the answers are molecular chemistry and single crystal X-ray diffractometry, respectively, applied to small nanoparticles. In other words, we were stimulated to try a bottom-up molecular approach to make things that are structurally small pieces of metal oxides. And I'd like to introduce you to the phrase we use, molecular nanoparticles. These are pieces of bulk solids as molecules. We're interested in metal oxides, of course. They must have, to be called molecular nanoparticles, they must have the same structure as the bulk material. Otherwise, they would just be metal oxide clusters. They bring all the advantages of molecular chemistry, because when you make a molecular sample, you have truly identical size and shape, solubility, molecular crystal formation, etc., to this area of nanoscience. And let me immediately say, before I get into what I'm saying, that the polyoxymetallates are not molecular nanoparticles because they don't have the structure of the bulk solids. So that was what we set out to do. Can we use our extensive experience with bottom-up, in other words, molecular synthesis, to make molecular nanoparticles of ultra-small metal oxides? And if we could, how similar to the top-down traditional nanoparticles will their structure and other properties be? And is there anything we can learn from them and use them for or traditional top-down nanoparticles. And I was stimulated by the report in 2007 and many papers since then that showed that you can do this for metals now. You can make a small piece of gold, that's the original paper, a small piece of gold with the same structure of bulk gold, but it's just a small piece and it's made as a molecule by using thiolate ligands. And it was published in Science. And that really stimulated me to work on this metal oxide area. The difference between metal oxides and, of course, the metals is the metals have metal-metal bonds. And in fact, that helps give you certain nuclearities of product because certain nuclearities bring along the right number of valence electrons to form all the metal-metal bonds that are needed for that nuclearity. So there's certain magic numbers that help. With metal oxides, we don't have metal-metal bonds. And so we wouldn't have that additional help. So it wasn't clear that we'd be able to do it. Now, we were after two metal oxides when we started. Cerium dioxide, because it's important to all areas of our modern society, and iron oxide, because it's so important to magnetism, to catalysis, to medicine, and so on. So we had the breakthrough in cerium dioxide. So let me tell you, cerium dioxide is probably the most important metal oxide that people don't realize on the planet. It's in every catalytic converter in cars, where it's a co-catalyst and also support for the rhodium, palladium, platinum catalytic metals. It's used in chemical mechanical polishing, as a catalyst in the water gas shift reaction. It's used in solid oxide fuel cells. But in particular, in the last 15 years, there's been a massive explosion of interest in nanoparticles of cerium dioxide, which are called CNP here. They're used in solar cells, oxygen sensors. This attracted me. Medical applications, you really want small nanoparticles for this, and they're important and being explored for medical applications related to damage from dangerous radicals. And then, low temperature catalytic of heavy petroleum, they're very much used in the petroleum industry for that reason. So we set out with the simple objective, simple to state, not so easy to accomplish, of making cerium dioxide nanoparticles, what I call ultra small ones, as molecules. So we could keep all the advantages of molecular chemistry. And small ones like cerium-6, there were several already in the literature, but these are too small to really think of as nanoparticles. And there were a couple of others a little bit bigger from Paul Kogler's group. But what we wanted was to get to really bigger sizes, and slowly we made 16 and 19 metal nuclearities, but then broke through, so to speak, into larger ones, 24, 38, and 40. And of course, this general size regime of 1 to 3 nanometers, roughly, there's a word called nanoclusters that's often used. I don't like this myself because I think it's too general term. But this small size regime is attracting attention. Of course, as you get bigger, you would go to nanoparticles. The title, by the way, is left here deliberately blank because can I call these molecular nanoparticles? Well, as I told you, you have to see whether the structure is what you have in the bulk solid. So what's the structure of bulk cerium dioxide? It's the fluoride structure, which has layers of gold-colored cerium 4+. It's a coordinate surrounded by tetrahedral oxide, which itself forms layers. And just looking at the compounds that I showed you on the previous slide, you can see I've made the oxygens very small to emphasize the layers of the cerium. These have the fluoride structure. They are small pieces of cerium dioxide. And so in a way, we have made pieces of cerium dioxide as molecules. And so we can go back to that slide, add the title that is now appropriate, change that nanoclusters to molecular nanoparticles, and now we can ask all sorts of questions. What are the favorable nuclearities? What factors can alter the product identity? what environments do the surface cerium 3 plus ions occupy? I forgot to mention, when you see blue here, it's cerium 3 plus. The gold color is cerium 4 plus. How does catalytic activity vary with size and cerium 3 plus content? Where are the protons located? It's almost impossible to identify proton positions in traditional nanoparticles. How are you going to detect them? So all these things now become possible. Let me point out the faces of cerium dioxide. These are the low index faces of cerium dioxide, the 100, 110, and 111. And then there's cerium dioxide itself. And then if you look at the cerium 40 from different viewpoints, you can see that they do indeed have the same face appearance. But one of the referees of our original paper that you see at the bottom there pointed out that if I wanted the nanoparticle community to accept these as real nanoparticles, I should show the pictures as they expect to see nanoparticles, not the way an inorganic chemist would. So we decided to start showing them in this representation, showing the surface facets. And these color codes are related to the things up there. So the blue squares are the 100 facets. The 111 is the green color, these hexagonal systems. And the 110, we don't see that very often, but we see it in the cerium 40, for example. So these really are cerium ultra small nanoparticles, cerium dioxide ultra small nanoparticles. Except we can now get crystal structures. These things that I'm showing you are all from single crystal X-ray crystallography. And so we're seeing everything to atomic resolution, and we can identify all aspects of these things. So if you're wondering how we identify oxidation states, well, EPR tells us there's cerium 3 plus there, because cerium 4 plus is diamagnetic. Von valence sum calculations on the metal confirm which cerium are actually cerium 3 plus. You can see cerium 4 here, which is that one there, plus its symmetry related partner over here are cerium 3 plus, and then all the others are cerium 4 plus. Also, we all know what a molecular crystal looks like, don't we? But I just show this to emphasize that this crystal contains nanoparticles of cerium dioxide, which are all exactly the same size and exactly the same shape. So this really is a truly monodisperse, in other words, single size sample of these materials. And also, we can identify surface features, which are really important to the catalysis people. We can see how the monolayer shell of organic ligands is binding. And we use carboxylates because they, of course, are related to the long chain carboxylic acids, often used as surfactants by the nanoparticle people. And so the carboxylate also is a very versatile ligand, and you can see that the different ways the carboxylates are bound in these clusters. And you can see that they can chelate or they can bridge 2 or more metal atoms. And it's particularly useful to have this versatility because with, of course, these small materials, you have areas of of high curvature, and you have areas which have low curvature. So ligands like carboxylates, which are very versatile and can adopt various bridging modes, are perfect to be able to cover the surfaces in high curvature and low curvature situations. And we can also characterize surface features, things bound on the surface, or such as cerium 3 plus, and also this purple here is a hydroxide. In other words, this is a site for protons, and the dashed lines are indicating that it's not really forming bonds, it's just an electrostatic interaction. And in fact, these squares, which are, if you go to the middle or the right, these are these blue 100 squares, which are known in the catalysis literature to be the very active sites for catalysis. And we can see these species on the surface are really basically oxygen defect sites because this hydroxide is not really bound there. And so we can identify, in other words, sites that correspond to the highly active catalytic sites in nanoparticles, but now we can characterize them to atomic resolution. And there's always something capping these in the resting state. I mean, these are resting state molecules. You can imagine under catalysis conditions, these ligands can move out of the way and then catalysis can occur. There's always something in the middle. Here, a chelating carboxylate has tilted over, so one of its oxygens is where the hydroxide was over here. And we can even see that with a ligand, with a solvent molecule. Here, this is an acetonitrile molecule on one of the serums, and you can see how it's dramatically tilted over the center of this 1,0,0 facet, acting as what we call a lid. When, of course, under catalysis conditions, this can get out the way or detach, and then you've got a very reactive 1,0,0 facet for catalysis. And we can see the protons, which I said is almost impossible with nanoparticles, but here we can see them because we see them attached to oxygens. We can see where the hydroxides are. Either occasionally we can see they can be found in crystallography, or we often usually identify them from the hydrogen bonds they're making with perhaps a surface solvent molecule in the lattice, and also from the oxygen BBS. We use oxygen BBS to indicate to us that there's a proton attached to the oxygen that we're not seeing. And this slide also shows how the protons tend to accumulate near the cerium 3+. And let's just go to this one on the right, which is extremely clear. There are 8 protons on the surface of this nanoparticle, and 4 of them you can see are on the left. I changed my color code. Hydroxide is now green. So the protons are accumulating near the cerium 3+, and the other 4 are near the other cerium 3+. So you can see why the cerium 3+ sites on nanoparticles, which are known to be extremely reactive sites, they're so reactive. The cerium 3+ is a source of an electron. We have protons congregating there, and we have these defect sites that can be very reactive. And if there's no cerium 3+, the protons spread out. You can see the green here, they just spread out. There's no cerium 3+, so they just distribute themselves symmetrically all over the place. All right, so the point I'm trying to make here is we can identify and characterize these surface units to high precision. And just to emphasize what I was saying earlier about the cerium 3+ sites being very reactive, they have fewer oxides. You can see that we have hydroxides instead. And you can see they're more kind of, what's the right word? They're more weakly bound to that surface. So the whole unit here is acting as a highly reactive system on the surface. So we're seeing these crucial catalytic features. We'll be seeing something else later involving magnetism. So I'm just, as I said to you, I'm laying the foundation for what this project is involving. We've done some reactivity. I won't go into too much detail because this is not the type of symposium where for catalysis, but we did want to compare the reactivity of our systems with the nanoparticles because there's very large use of cerium dioxide nanoparticles in medicine, especially for mopping up dangerous radicals and avoiding neurodegenerative problems like Parkinson's and other strokes and other things. So with the nanoparticles, you can follow, there's a spin trap you can use. You can generate hydroxy radicals, which are, of course, very dangerous. The hydroxy radicals will form a spin trap with this organic molecule. So you get this radical on the right-hand side here at the bottom. And then by following the EPR of this radical, you can see how much you have and how it changes with time. So here's a plot from the nanoparticle literature. But I won't go into too much detail on that, except to show you that we can do the same thing with our molecular nanoparticles. Here's one example of the sort of EPR study we do. This is a time dependence of the EPR spectrum, and it decays with time. We can follow this for all these molecules to look for trends, because now we're doing this experiment with a single size and a single shape. So this is different in many ways from the nanoparticle studies, which always use a range of sizes and shapes. And you can see the black here, by the way, is the blank. That's if there's no nanoparticle clusters there. And then you can see that some of our molecules are terrible scavengers. And some, these ones at the bottom, even in the first EPR spectrum we take, we see no EPR signal, because the clusters, the cerium clusters, have scavenged all the hydroxy radicals incredibly efficiently. And when we start looking to see for a trend, the trend we see actually is that the more cerium 3+ that's in these molecules, at least for hydroxy radical scavenging, the more cerium 3+, the less the activity. The cerium 4+ compounds that only have cerium 4+, in other words, are so reactive they all give these baseline signals. In other words, you don't see any EPR. The hydroxy radicals are destroyed so efficiently. And that's been published if you're interested in that. But let me get back to the idea of using this molecular approach to make nanoparticles, because more recently we were able to extend this to 2.4 nanometer dimension systems. And this is really now much more realistically similar to ultra small cerium dioxide nanoparticles. The previous work was a foundation. Now we're really getting to the sizes used with ultra small nanoparticles. It's sort of 2 to 10 nanometers. This one has 2.4. We were able to get crystals, molecular crystal. I mean, here we are. We've got identical molecules in there. And it shows this beautiful high symmetry core. It's D2, and it looks like a sort of a fattened tetrahedron. It looks like a pear shape, but if you rotate it by 90 degrees, the thicker part is at the bottom. This is a beautiful D2 symmetry nanoparticle of cerium dioxide. We're already exploring a lot of other things, because the surface to us is important, and you'll see why in a moment. There's evidence in the nanoparticle literature that simple ions like chloride and nitrate can affect the shape of the nanoparticle and the activity of the nanoparticle that you get. So we have explored the same thing with our materials. And with chloride, we get a completely different compound with a lot of cerium 3+ in. So this is really giving us nanoparticles with lots of these reactive cerium 3+ sites. And with nitrate, again, we get things, it changes the structure of the product, but less so. We have just 4 cerium 3+ in them. And what they do, the cerium 3, the chlorides bind on surfaces and actually inhibit growth. It's as simple as that. Here's the cerium 24 I showed you earlier. And if we compare that with the cerium 20, we can see that the chlorides have stuck on the surfaces and prevented the top and bottom layer from forming. So the cerium 20 is really just in the central 3 layers of cerium 24. We are inhibiting growth in certain directions and giving, therefore, different morphologies of the nanoparticles, and in particular ones with lots of these cerium, these 1,0,0 blue facets, which are very reactive in catalysis. All right, so that's the foundation I was talking about. Can we use molecular chemistry to make ultra small nanoparticles, so we can use all the molecular advantages? One of the things I mentioned about small nanoparticles is that people put metals on, including magnetic molecules. So that's where we've been moving in the last 18 months or so. Here's one of those cerium nanoparticles. This paper's in Press in Inorganic Chemistry. It's it's a cerium-23, but it's actually a cerium-19 octahedral nanoparticle. And on the surface are these green manganese 3+, and the pink here is manganese 2+. So we have these little magnetic units on this cerium nanoparticle. And that is an example of what we want to do and what we are doing now, and that is to put magnetic units on these nanoparticles as sort of models for magnetic units on surfaces, or for larger nanoparticles. But now, because it's all molecular, we can characterize these to higher precision. So the other thing I said is that we were after iron oxide many years ago. Well, we've returned to them now. And once we got that cerium dioxide foundation in place, we've gone back. I don't have time to go into this in detail, but we've now broken through into clusters of iron oxide, which have the same structure as iron oxide. This one that I'm showing you here is the structure of gamma iron oxide, which has the spinel structure. And on the surface are these blue lanthanum 3+ ions. These are diamagnetic, of course, lanthanum 3+. It's a very high symmetry species. The iron oxide unit is spin s=7. Lanthanum is diamagnetic. If you look at it from the top, you can see the 6 lanthanums form this beautiful hexagon on the surface of the iron oxide molecular nanoparticle. We've also done it with magnetic lanthanide ions, and you can see we've done it with praseodymium, samarium, gadolinium, terbium, and dysprosium in this plot. And over here, the iron 7 unit and the praseodymium and samarium have these 3 lower KMT plots. What's interesting, though, is when we go to terbium and dysprosium and gadolinium, we get ferromagnetic coupling between the lanthanides and the iron oxide core, and you can see that take off at low temperature. And we can also see we can also see the AC data, and we see the sort of drops you expect for a single molecule magnet, and out of phase signals here showing that there's a barrier. And these are, by modern standards, are not great single molecule magnets, but remember the single molecule magnets on this iron oxide surface, which is what we're interested in. And then you can also see hysteresis loops for these terbiums on the surface. So the idea of now putting magnetic units onto these molecular nanoparticles is what's taking most of our time. We've also extended this work to epsilon iron oxide. I won't go into this. Epsilon iron oxide is a rarer form of iron 3 oxide, but one with important magnetic properties. What I want to finish with is what I promised you, and that is going back to magnetism again, as I did now with the iron oxide. We're also working with bismuth oxide, and we've made molecular nanoparticles of delta bismuth oxide, which is actually a high temperature form of bismuth oxide, and yet at this molecular nanoparticle size regime, it's the one that's stable at room temperature. And what I want to show you is that we can put manganese on the surface, and those are the green atoms. Okay. Let me just what I want to show you is that these manganese units, there's 2 I'm looking at the 6. They're in the plane around the bismuth oxide. We have 2 dinuclear units, rich by an oxide, in other words, and then we have 2 mononuclear units. And when we look at the KMT, it's a bit noisier than normal, but these are gigantic molecules. We can see characteristic KMT versus T plot of a ferromagnetically coupled system. And if they were non-interacting, we'd be down where this blue dashed line is. So it looks to us like we have ferromagnetic coupling in the dinuclear units, and then of course the mononuclear units are just S=2 manganese 3. But what was interesting was at very low temperature, when we went to in-phase AC, we saw a distinct drop in the chi prime MT, suggesting that there was an interaction between these units, the manganese units. And you may, as we did originally, think, well, is there really going to be an interaction between this dinuclear unit and a unit that's 4 bonds away? But we've already published papers showing that sort of thing can really. Wait a minute, what happened to it? Oh, all right. So I'll get back to that. So there, we looked at the hysteresis loops. This is Wolfgang Wernsdorfer in Germany. And he was able to show that these dinuclear units are showing hysteresis. And they even show a quantum tunneling of magnetization step at 0 field, which is, you heard about quantum tunneling in the previous talk. And what we're seeing here, in other words, is a hysteresis loop for a single molecule magnet on this bismuth oxide nanoparticle. And we can see, of course, that from the crystal structure that the dinuclear unit is this. And some of you who are familiar with manganese systems may recognize this as being a common type of unit in manganese 3+ chemistry. There are many dinuclear compounds that have 2 manganese 3+ linked by an oxide and 2 carboxylates, which is exactly what we have here. Except now the oxide is attaching to bismuth and the carboxylate is attaching to bismuth too. So we're seeing how this magnetic unit is attaching to this metal oxide nanoparticle support. The idea, and yeah, this is a little bit out of order, but anyway, the idea that magnetic units separated by 4 bonds can be interacting. We published a paper just recently showing that's possible. Here we had magnetic units, manganese at one end and a dinuclear manganese at the other, separated by these diamagnetic cerium ions, and yet we had a significant interaction between them through 4 bonds, and the whole molecule behaves as if it's got just one magnetic unit on with a spin S equals 17 hards. And you can see that in the magnetism when we fit the data and we sorted all that out. And we see it in this smaller unit too. There's a significant interaction between this dinuclear unit at the bottom and the manganese at the top that gives us basically a single magnetic unit. Now I want to finish this by showing you another one of these, because this time there's no mononuclear unit, so things are much clearer. And we're doing for time. I guess I'm just about finishing. This compound here is again a small piece of delta bismuth oxide. It's got a defect fluoride structure. It really just looks like delta bismuth oxide, trust me. But now we have 8 manganese on the surface, and there, if I make the bismuth small, you can see that the 8 manganese occur as 4 dinuclear units now. We don't have that mononuclear sites anymore. And they're arranged at approximately the corners of a tetrahedron, but they're not symmetry equivalent. They're not strictly symmetry equivalent. And they're separated by 4 bonds, some of them. Some are separated by 6 bonds. And yet we see the interaction between them because it shows up. First of all, we see hysteresis. And then we see clear evidence, if you look carefully, of steps in this, which are coming from interactions between those dinuclear single molecule magnets. This is the exchange bias quantum tunneling of magnetization effect that we originally published back in 2002. And if you look at the first derivative to make it clearer exactly what's going on in these hysteresis loops, you can actually see, I mean, on the left, you can see, if you look carefully, that it looks like before you get to 0 field, there's one step there, and then another one here, and then another one, and then another one. There's 4 steps there. And that is the characteristic signature of a single molecule magnet actually interacting with 2 others. And if you look at the first derivative, then it becomes pretty clear that you have 4 features in that hysteresis loop. And it's not ultra symmetric. Why not? You can see the spacings are not all the same, because the 4 dinuclear units on the surface are not symmetry equivalent. So this is 4 single molecule magnets on a metal oxide nanoparticle interacting, showing hysteresis, but also showing they're interacting with each other to give an exchange bias shift of the steps due to quantum tunneling of magnetization. So if I summarize, what we've done here is structurally characterize single molecule magnets on a metal oxide surface by making the surface part of the molecule, so to speak. We have a molecule where it's surface plus single molecule magnet, and then the whole thing can be crystallized into a single crystal, a molecular crystal, so you can get structural information. You can see the hysteresis as well from the single molecule magnets, and you can even see the quantum tunneling exchange bias effect of the quantum tunneling, showing that they're interacting. And people who follow interacting single molecule magnets knows that exchange interactions between single molecule magnets give quantum superposition states and quantum entanglements. So the whole thing is structurally characterized to atomic resolution. And we're doing other things with magnetic molecules on surface, but I've run out of time. So let me just summarize that molecular chemistry is a powerful bottom-up approach to ultra-small molecular nanoparticles. We often get the rare forms of metal oxides, which is interesting. And the whole thing, as I just said, is an approach to surface plus attached magnetic units. So with that, I'll finish. I took work by these people in blue, and I acknowledge Professor Wernsdorfer at Karlsruhe Institute of Technology and his student Michael Schulze, and our funding by NSF and the Department of Energy. I took work by both those funding sources. So thank you for your attention.
Thank you very much for this absolutely fascinating lecture and fantastic moieties, molecules. And the lecture is now open for comments, for questions. Jakob, before they appear, let me ask my question. What actually Faraday did was he took a magnet and put it into metal coil. Do you think that with your magnetic molecules, would it be possible to somehow mimic his experiment? I mean, to put those magnets, to couple them with some organic conductors and move those magnetic molecules in order to generate, for example, current in this magnetic conductors couple?
Well, I don't know, but it sounds exciting. That would be a fascinating application. I don't know, Christou. I guess, as I tell my students, you can't really say something's possible until you do it. So
yes,
I don't have the skills to be the one to try things like that, to be honest. If any physicists want to think along those lines, I'd be happy to provide materials.
Thank you. Dietmar Stalke. George, how do you synthesize those giant clusters? How can you control nuclearity? Is this wet lab chemistry, like the work of, for example, Dieter Fensky, or is this high pressure, high temperature, solid state work?
Okay, thank you. I avoided synthetic discussion just because I knew I wouldn't have time, but this is all wet chemistry. It's in solution, typically at ambient temperature, room temperature, or slightly above. And we use basically all the usual tricks of solution chemistry, solution molecular chemistry. What we've found in the last 30 years or so of working with manganese single molecule magnets is that what you get is of course under thermodynamic control almost always, and things like the bulk of the carboxylate and the polarity of the solvent are very important to the assembly of a product. And changing bulk or changing solvent is one way that you can vary product nuclearity and maybe symmetry and so forth. And so, of course, we had extensive experience from manganese cluster chemistry over all these years, and we applied all these things, what we call standard sort of synthetic approaches. And to be more precise now, with those cerium dioxide molecular nanoparticles that I started to talk with, and by the way, I mean, they are historically the first, and they're the ones that showed us this approach works and we should push it as far as we could. We found that the carboxylate was particularly important. The solvent was almost always just a mixture of pyridine and water. I mean, all the details are in the papers, in the references that I gave. And what was really changing the product nuclearity was the carboxylate bulk. This was all done under ambient pressure, almost always at room temperature, and then it was just isolation of product, often by the usual sort of crystallization methods, layerings, and so on and so forth. So no high pressure work, no. This isn't solid state chemistry or anything like that. It's just wet chemistry, and we don't even have to worry about Schlenk lines. Usually, it's just open to the air. We want water around because water is where a lot of the oxides come from.
Thank you very much. Now, Jakob says, wonderful molecular chemistry. Do you see a lot of disorder in the structures?
No, not a lot. No, we don't see a lot. I mean, we see the usual kind of thing. Sometimes ligands that maybe have rotational disorder. Typically, we might see a little bit of that. But these are minor effects, and the cerium 3+ positions are always ordered because, in fact, the environment of the cerium 3+, as I showed, is different from the cerium 4+. So that, of course, orders the cerium 3+ in a particular position. We've seen some disorder in the proton positions, which isn't surprising because we know even the nanoparticle people have long known that protons are mobile on the surface of their nanoparticles. And so if protons have a choice of symmetry equivalent or near symmetry equivalent surface oxides they combine to, then it may vary from molecule to molecule. In other words, we'll see static disorder of some of the protons. But it's really, that's all the kind of disorder we see. We don't see mixtures of different sizes, disorder in or fractional occupancy of some of the metal positions, suggesting that we have different nuclearity clusters there. These are all well refined, and I mean, they are exactly identical. It's the power of molecular chemistry and thermodynamic control. It's just beautiful.
Thank you. Uli Englert, thank you for this excellent talk. Your nanoparticles are not only atom precise, but also oriented, at least as long as you look at a single crystal. This is probably difficult to achieve top down, right?
Well, I mean, yes, the molecule, they're nanoparticles, but they're first and foremost molecules, and so they pack into a molecular crystal, and highly ordered molecular crystal. They aren't all necessarily oriented exactly the same. The picture I showed had, for example, a slight tilt between neighbors, but I mean that's just irrelevant, really. The molecules themselves are exactly the same. And I mean, it's molecular chemistry. The crystals are growing, and the packing is controlled by the crystallization kinetics and the various factors that that control packing energies. So it's they are exactly identical and oriented, not necessarily all parallel, but oriented in an ordered manner.
Could you please allow Kaczynski to ask question himself?
Okay.
George. Piotr, hello.
Yes, hi, how are you? Good to see
well,
you.
thank you. Good to
Fantastic
see.
Lecture and beautiful systems. I always admire your clusters or molecular systems that you are working with. So I have, being organic chemist, I have a question. I cannot avoid asking questions. So you work with benzoic acid as the cupping, in a sense, like a cupping system. Do you see more role for more advanced, more let's say, systems of carboxylic acid with more functionality, including even spin, like carboxylic acid radicals?
Oh yeah, there's a lot of potential in this area, and I basically touched the surface of what we're doing. We've been using a lot of different carboxylates, and there's a parallel area that you may have heard in the introduction that we've been working with, and that is molecular nanoparticle of the manganite perovskites. In other words, mixed metal oxides. What we're doing there is exploring various carboxylates, not just the simple ones that I showed in the talk, actually, but things that may have conjugated aromatic rings like naphthoic acid and anthranilic acid and larger carboxylates. Because we're also interested in some photochemistry. So there's a variety of different organics that we're investigating. And ultimately, the rate determining step, I guess I can call it, is whether we can find ways of isolating and crystallizing these things. Because as you can imagine, unless you can get a crystal structure, then you don't really know what reality is. There's some evidence that we're beginning to get experienced at seeing from infrared that it might be a small cluster or a big cluster, but without crystallography, we can't identify the product. So yeah, some of these carboxylates give nice structures and some don't. We also, you talked about functionalizing them. We've been using things like aminobenzoates for a number of reasons, including trying to set up some hydrogen bonding networks between the molecules. That's coming along, but I don't include it in talk shed. It can be really when you have amino systems there, then they can get protonated and give us intermolecular hydrogen bonds, and it's not so straightforward to process the molecules and crystallize them, unfortunately.
That's great. Thank you.
Thank you. Saravanan Kandasamy. Great work, Professor. What is the difference between quantum dots and molecular nanoparticles apart from its size? How molecular nanoparticles are beneficial compared to quantum dots?
Well, I mean, in many of the molecules I showed you, we had a diamagnetic system. We haven't really. I guess back in when I was in single molecule magnets, more or less full time, we would occasionally call them magnetic quantum dots. I don't think that name ever really stuck. I don't think I would call my systems now these molecular nanoparticles quantum dots. I think it might give the wrong impression to people what they are and what we're after in particular. Again, some of them are magnetic, so and we can add electrons, we can reduce them. I mean, iron 3+ is easily reduced, so there are various ways that that language could be, I suppose, relevant, but we don't use it.
Okay, thank you very much. Dietmar Spalke, CO2 is pretty insoluble. So, so you generate that in situ, right? Dioxide.
Oh, cerium dioxide? Well, we don't actually make cerium dioxide in the sense that what we're making are small nanoparticles as molecules. So these molecules are individual entities, and so they are completely soluble because of their monolayer organic shell. If we had a, you know, probably if we destroyed them with acid, they might convert to cerium dioxide, and then yes, we would have a very insoluble precipitate coming down. But we'd never see. Maybe this is what the question's about. We never actually see cerium dioxide forming in these reactions. We start with cerium salts, just cerium ammonium nitrate or cerium 3+ chloride or 3+ nitrate. And we do reactions between a cerium source and a carboxylic acid in the presence of a base, which could be pyridine as a cold solvent or added triethylamine. And these molecular units assemble. They grow bigger, and under the conditions of whatever the conditions are, they stop at a particular nuclearity. And as I said before, by changing the carboxylate and the conditions, we can get them to go to different nuclearities. But we never see cerium dioxide under these conditions. So, of course, we add strong sodium hydroxide or something. I remember now in the past we have got cerium dioxide when we use sodium hydroxide, so that's why we don't use it anymore.
Professor Hans-Bert Birgi, do you know what the mechanisms of formations are? Reaction intermediates?
No, and I would not even venture to guess, because I'm sure they're incredibly complicated. Assembling something that's even got just 20 ceriums is probably a very large multi-step process. But what I will say is that some people have asked me why. I say that we can use different carboxylates and get different products. And people would say to me, well, why? Why does benzoic acid give you a different sized product than acetic acid? And this, to me, the nature of the carboxylate is probably affecting the product, because the bulk of the carboxylate and maybe its properties as reflected in the pKa, for example, are allowing different sort of intermediates to form, and therefore the aggregation pathway goes along a different route and gives us a different product. So clearly the carboxylate is probably influencing this multi-step aggregation procedure that's converting simple cerium salts into a large cerium oxide cluster. And but to speculate, well, it would be speculation. Presumably, it's going through the cerium 6-octahedron, which is already known, and then another layer will form on top. What the mechanism of that formation is, I have no idea, and so on.
How long does it take? I mean, the reaction itself. It's minutes, hours, days?
We typically will put a reaction on and leave it overnight. And then some of them we leave longer. Actually, the slowest part of this is growing the crystals. The molecules are getting so big that it's almost like crystallizing small proteins. And it's a slow process. The cerium 100, for example, I mean, originally when we first made it, the student, who was actually an undergraduate, almost gave up and poured it into the waste bottle, because it had been on his shelf for something like 6 weeks and he couldn't see any crystals coming out. And then he started seeing some crystals grow. And once they started, they seemed to form fairly quickly. So after about 2 months, we had a really nice sample of the cerium 100. Once you know something's possible, then you find a way of speeding it up and so on. And we often do now heat a little bit or change some of the other conditions. And we can get that procedure down to about 4 to 6 weeks. But again, it's the crystallization. We have to be patient with that. These are big, big, big molecules. And just like big proteins, you have to just take your time and give it, and just be patient and realize it's not going to crystallize overnight like small molecules often do.
Okay, thank you very much. Jakob is asking, to function as single molecular magnets, do you need to deposit them on surfaces? Are they stable enough to vapor deposit?
Okay, I assume he's referring to the bismuth systems. Maybe I went through it. Yeah, I didn't really talk about synthetic procedures. We don't make the bismuth system and then add the manganese. We actually do that in one step. By controlling the amount of manganese and the ratio and so on, and the conditions, we can actually generate these bismuth molecular nanoparticles with the manganese on the surface. And we do that also with the cerium clusters now. It's actually easier to have the manganese there to begin with, and we find cleaner products that way. So we don't have to take manganese single molecule magnets and do any kind of addition to the surface. Now that's obviously a direction we want to go, because once we have these cerium dioxide and bismuth oxide molecular nanoparticles, we can now pick and choose what single molecule magnets we might try and put on the surface. I'd like to, for example, try and put some of the single molecule magnets that people have been interested in for a long time. They often put the phthalocyanins, for example, on a surface, and then, of course, they can see them with STMs or some similar way. It would be nice to actually see atomic precision, a single crystal X-ray structure of these kinds of things on the surface. We did that with the lanthanides on the iron oxide, and it's really nice to see how the terbium, for example, is attached to the surface of the iron oxide. But it would be nice now to extend that to other systems too. But, you know, as I said, this is a fairly new project, so there's a limited amount of various directions we've had a chance to explore yet.
S.M. Tariq Abedin. Truly admirable and great work, Professor. I was wondering if I work with n times n molecular magnetic square grid molecules by strict ligand design, what sort of interaction can I expect with the cerium systems? Can you comment on this, please?
So you're working with two-dimensional molecular grids, is that
yes,
what?
n times n molecular magnetic square grid molecules. That's
very interesting. And the question was whether they would interact with the cerium dioxide systems.
What sort of interaction can I expect with the cerium systems?
Well, if your grids contain the metals in a that would like to bind to oxygen, perhaps, then it's possible that you could, just like the manganese systems I showed you, you can deposit these grids on the surface of molecular nanoparticles. It would that goes back to my previous question that what we're trying to develop now is making the cerium nanoparticles first and then depositing molecules of choice on, and then to characterize how they're attached and are they being distorted by being deposited. So if you have some molecular grids, I don't know how big they are that you're working with, but if they're fairly small, I don't see why they wouldn't be able to sit on the surface, as long as there's some kind of potential for them to interact with the surface if they like to bind to oxygens, for example, that kind of thing.
Okay, thank you very much. Are there any more questions or comments? If not, let me finish by asking the last, my own question.
Sure.
You mentioned that you were not extensively using pressure, but why not? Pressure could be a source of change of your systems. You can generate, say, reaction changes of surfaces, etc., etc. I think that would be a great stimulus to apply for these beautiful systems, really.
Yeah, no, I think you're absolutely right. It's just a matter of what procedures we're using and what equipment's available to us and things like that. But I mean, when it was first mentioned, I thought that's an interesting thing to explore, because I'm sure we're also, by the way, along similar lines, we're exploring using microwaves to see how they control the cluster aggregation and what the product is. But you're right. I think pressure is a very attractive external perturbation. I think it would be nice to try and incorporate that into our work.
And the very last question, you were showing most of your beautiful clusters were, I would say, homoclusters. Is this feasible to make, like, say, strongly heteroclusters when big chunk of those clusters consist of quite different atoms? Is this has anybody been doing this kind of?
So, are you saying that can we make clusters where you have maybe one part of the molecule is cerium and another part of the molecule is some other metal? Okay, yes, we're working in that area, and the reason we're working in that area is that in industry, they often use mixed metal oxide catalysts, and they find that the mixed metal oxide catalysts are more reactive than either metal oxide by itself. And what they found is that the two phases don't mix. So when these are not really mixed; they're composite. In other words, they have, and one of them is actually a mixture of cerium dioxide and manganese oxides. But what you find is that you have areas of just cerium dioxide, and then attached to them will be a small piece of manganese oxide, and so on. You have phase separation. But nevertheless, where they fuse together, that's supposed to be where all the very high catalytic activity comes from. So again, since we're using a molecular approach, we're trying to find molecules now that have two phases joined together, like you just described. And one way that we're thinking of doing it is to build on those experiments that give us the cerium dioxide with manganese on the surface. So we're now increasing the manganese to try and get bigger pieces of manganese oxide attached to the cerium oxide. So maybe either as a core shell, I know that's very popular in traditional nanoparticles, to have a core of one metal cyanide or whatever it might be, metal oxide, metal sulfide, and then around it have a shell of some other metal oxide or metal sulfide or whatever. Or it could be attached next to each other. And I should also say that one of the other, so we're doing this with manganese cerium, but also another area is mixed things like cerium and titanium oxides, which are also extremely important in industry. And again, there seem to be two phases present, and where those phases meet is where the highest catalytic activity is to be found. So these are all things that I think, yes, Christoph, I think we can do them. I think it's just like any synthetic project. It's figuring out the exact conditions and so on. And then ultimately, of course, being able to prove it by getting molecular crystals of these things.
And the very last question from Hans-Bert Birgi. Does any of your molecules have catalytic properties?
Yes, I mentioned the ones we've been concentrating on because of their medical relevance. We've done a lot of hydroxy radical scavenging because I think it would be great. I mean, these very small nanoparticles of cerium dioxide are being used in biomedical research. But when you start using nanoparticles in medicine, of course, you have to worry not just on activity, but also on toxicity. And depending on the size and depending on the shape and depending probably on the cerium 3+ content on the surface, some nanoparticles show toxicity, and so this is a problem. Now, if we can make molecular nanoparticles, which we can, of particular size and composition, then this issue can hopefully help solve the toxicity issue and identify the right sizes that would allow. I mean, they're being used for various therapies, including anti-tumor activity. So if we can characterize their medical activity as a function of size and shape and cerium 3+ content and so on, then I think we can make a significant contribution to the biomedical research. So that's why we're concentrating on hydroxy radical scavenging. We haven't used them for things like CO oxidation or some of the other things the industrial people are interested in. Although that's something we could do now. Again, it's just a matter of resources and how many hands you have in the group and things like that, and how much money, of course.
Thank you very much. As I do not see any more questions nor comments, let us thank again Professor Christou and Professor Overgaard for these two excellent, really beautiful lectures.